Hey there, this is part 2 of our mean value theorem video series. So we have this example. Suppose that 3 is less than or equal to f prime of x less than or equal to 5 for all values of x. Show that the function, so f of a minus f of 2, is between 18 and 30. Okay, so at first this looks a little random and somewhat intimidating, wouldn't you agree? So how do we tackle this? Okay, well, one hint is that I know I'm in the mean value theorem and Rolle's theorem section, so I'm gonna try to go with that. And so I look at the first part. It's like, okay, so it says the derivative, so f prime of x is between 3 and 5. Now notice that it says for all values of x. So all values of x, to me, that means minus infinity to infinity, right? There's no restriction. It says all values of x. So that means that the derivative is always between 3 and 5 for any value of x, but most importantly, it tells me the derivative exists. So f prime of x exists on, for all values of x, so on minus infinity to infinity. And from here, now we can use the theorem that if the function is differentiable, then the function is continuous, right? Because what this means is that f prime of x, or that f is differentiable. So since the derivative exists for all real numbers, then that means that f of x is differentiable on all real numbers, all values of x. So if it's differentiable, then we can say f of x is continuous. And that was that theorem that we had when we started derivatives and talking about what it means to be differentiable. There was a theorem that said if the function is differentiable, then the function is continuous, but the converse is not true, right? If the function is continuous, that does not mean the function is differentiable. Think the absolute value of x. But because the function is differentiable, we can say then the function is continuous. So we have that f of x is differentiable on all real numbers, and f of x is continuous on all real numbers. Now, for Rolle's theorem and for the mean value theorem, we need to really get our hands on a closed interval. Open minus infinity to infinity open interval doesn't help us with Rolle's theorem or the mean value theorem. We need to get our hands on a closed interval. And so now I'm gonna go and focus my attention on this part of the problem. Notice that I have f of 8 and f of 2. So that kind of is looking like an f of b minus f of a, right? So because I see that, I'm going to say, well, because f of x is differentiable on the entire real line and is continuous on the entire real line, I'm going to make the claim that f of x is continuous on the closed interval to 8. Right? If it's continuous on the entire real line, it's definitely continuous on the closed interval. And because it's differentiable on the entire real line, I'm going to say f of x is differentiable. So I'm going to abbreviate things here on 2 to 8. So cont means continuous, diff differentiable on 2 8. I know what you're wondering, why the 2 8? And that was just it. This is actually a really fun problem. It's like a little puzzle. It's like, okay, this tells me, right, the first part, the derivative being between 3 and 5 for all values of x tells me that derivative exists. It's not very exciting. It's always between 3 and between 5, but it exists for all values of x. And this part kind of guides me into there's an f of 8 and an f of 2. And that looks like f of b minus f of a to me, so that's where the 2 8 is coming from, my ab. So because, and why am I choosing an interval? Because Rolle's theorem and the mean value theorem require a closed interval for continuity. So I need to get my hands on a closed interval, so that f of a 8 minus f of 2 help me get my hands on the closed interval. So I don't know anything about f of 2 and f of 8, so it's probably not Rolle's theorem, but I have the two conditions for the mean value theorem. F of x is continuous on a closed interval, and f of x is differentiable on that same open interval. So therefore, I can say Therefore, by the mean value theorem, there is a c in the open interval to 8 such that f prime of c is equal to f of b, so f of 8, minus f of a, so f of 2, over b minus 8, over 8 minus 2. And so now that's starting to look more like, oh, now I can see where my f of 8 and my f of 2 are coming in. So we're assuming that this is true, which is what led us to say all these things. It's differentiable, it's continuous, and well, we're trying to show this. So I don't know that this is true. I'm trying to prove that this is true, but so that gives me a way to get my hands on 2 and 8. So now let's see, we're supposed to prove that this is true. So what do we know? We know from the assumption that f prime of c is always between what two values? It's always between 3 and 5, right? But we just found a value for f prime of c, right? F prime of c is equal to this. So let's substitute that in. And so I'm going to have 3 is less than or equal to f prime of c, which is f of 8 minus f of 2 over 6. And that's less than 5. Ta-da! Can you see it? Do you see it? Are you excited? So now I can multiply everything by 6. And we get 6 times 3. Oh, my parenthesis is a little off there. 6 times 3 is 18. And 6 times 5 is 30. So I'm going to have 18 is less than or equal to my f of 8 minus f of 2, which is less than 6 times 5, which is 30, which is what we wanted to prove. Show that 18 is less than f of 8 minus f of 2, and that whole thing is less than 30, less than or equal to 30. Forgot my equals here. So we were able to prove that. So it starts off a little random and like we don't know what to do, but once we start kind of thinking about our theorems, okay, I know that derivative is, I'm being told that derivative is always between 3 and 5 for all values of x. So this was the big thing. It says for all values of x, so that means on the entire real line. So that means that derivative exists on all real numbers. So that means that the function is differentiable. So if the function is differentiable, then the function is continuous on the entire real line. And then I need to get my hands on an interval. So how do I get my hands on the interval? What I'm trying to show is something about f of 8 and f of 2. So I'm going to look at the x values 2 and 8. And so that's where my closed interval comes from. And then I just go putting the mean value theorem together. And then using our assumption here. And we have proven that. All right, let's try our last example for this section, which involves a piecewise function. I hope that even though this problem appears intimidating at the beginning, I hope that you are able to find the fun in it, right? Like, I don't know, it's like when you solve a puzzle, when you're working on something and then you finally get it and you're like, oh, that was actually really cool. So that's one of these problems. It's just look at it as a little puzzle. All right, so example 5, let f of x be that piecewise function. Determine if the mean value theorem applies on the closed interval 1, 4. If it does, find the value of c guaranteed by the mean value theorem. So to check if the mean value theorem applies, that means we want to see is f of x continuous on the interval, the closed interval 1, 4, and then is it differentiable on the open interval 1, 4. So those are the things that we need to check. So let's check the continuity first. So looking at f of x, 2x plus 1, that's a line. 3x minus 2, that's another line. So you have two lines that you're putting together at 3. So we have a risk of this not being continuous at 3. So check continuity for x equals 3. So let's say check continuity at x equals 3. So remember our the checklist for continuity has the 3 conditions. So one is that f of 3 exists. So does that exist? Let's see, f of 3, where are we allowed to plug 3 in? We can't put in both, right? There has to be only one where we're allowed to plug 3 in, and that's the one with the equals. So 3x minus 2. So f of 3 will be 3 times 3 minus 2, which is 7. So it does exist. What about the second condition is that the limit as x goes to 3 has to exist. What does it mean for a limit to exist? That means that the limit from the left and the limit from the right are the same. So let's look at the limit as x goes to 3 from the left of f of x. You're following, if you're to the left of 3, you are less than 3. So we're following the top function. So it's the limit as x goes to 3 of 2x plus 1, which is 7. And the limit from the right, we're following the other function. The limit as, so be the limit as x goes to 3 of 3x minus 2, which is also 7. Are they the same? Yes, they're equal, so the limit does exist and the limit is 7. The third condition for continuity is that f of a has to be the limit as x goes to a of f of x, and this definitely checks, right? Everything is 7, so that means that our function is continuous. Is continuous on, our interval was 1, 4. The second part is we have to check that it's differentiable. So is f of x differentiable? So let me write out f of x again, and then we'll find a derivative. So f of x is 2x plus 1 when x is less than 3, and 3x minus 2 when x is greater than or equal to 3. So when you take the derivative, you take the derivative each piece. So the derivative of the top will just be 2 when x is less than 3, and it will be 3 when x is greater or equal to 3. And I can already see that the derivative is not continuous, right? So then that means that it is not going to be differentiable at 3, right? Because essentially this is saying that as x approaches 3 from the left, the slope of the tangent line is 2, but as x approaches 3 from the right, the slope of the tangent line is 3. So that means that we have a cusp over here. So it's not the same value. So probably when these two lines connect, they create maybe not a cusp but a corner. So they might create a corner, and that's why it is not differentiable. I guess they have positive slopes, so they wouldn't look like that, but I was just trying to create a corner. So they're going to create some sort of corner as they meet up. Even though the function is continuous, it is not differentiable. Again, kind of think of it like the absolute value of x, right? The function is continuous, but it's not differentiable at 0 because you have that corner right at the vertex of the v. So f of x is not differentiable at 3, and 3 happens to be on interval 1, 4. So it's not differentiable on 1, 4. So that means that the mean value theorem does not apply. In order for us to use Rolle's theorem or the mean value theorem, the conditions have to be met. So always, the big thing I'm going to emphasize is that when you're working on using Rolle's theorem or the mean value theorem, you have to provide a closed interval for continuity. So going back to the previous one, when I said, oh, this means that f of x is differentiable on minus infinity to infinity, so therefore it's continuous on minus infinity to infinity, I cannot use Rolle's theorem or the mean value theorem with an open interval like that. Especially at minus infinity to infinity, I have to have a closed interval. So you have to find a way to get your hands on a closed interval. So that is the big thing with both of these theorems. So I hope that these videos are helpful, and contact me if you have any questions.